Hi everybody. Today is the Tuesday, 22nd of June. So let's continue with problems, fields and webs in communication electronics by Ramo. This one is going to be chapter 3. So let's start with problem 3.8. They ask you to check to see which, if any, of the following could be phasor representations of fields are consistent with the Maxwell equation in a short free region. Well, since you have the fields in the phasor form, that means you don't have the time-dependent term. The time-dependent, actually, you get used to that. Actually, is the exponential of j omega t. Sorry. Now they ask you to consider three different fields: 1, 2 for H, and 3 for E in different coordinates. So you have rectangular, circular, and spherical. To check if all fields satisfies the phasor form of Maxwell equation or not, you simply check back to our Maxwell equation, which are curl E equal to negative j omega b, and curl H equal to j plus j omega d, where B is the magnetic flux density and D is the electric flux density. J is the current density, E is the electric field, and H is the magnetic field. Okay, in general, if I have Ex equal to the constant e to the j phi x, Ey equal to b e to j phi y, and so on for Ex. Sorry, Ez. So you can write the electric field in the x component and y component and z components as shown. And if for phi x equal to phi y equal to phi z equal to phi e, you can rewrite E equal to the phasor form, and that's the real vector. But if the phase anchors of the components not equal, you cannot put the fields in this form or the phasor form. Now let's make a move to check if fields will satisfy the phasor forms of Maxwell equation or not. That means you need to check and compare to the Maxwell equations. For I, E given equal to unit vector x, C is the constant, exponential negative j omega square root mu or epsilon z, or actually E has only x component and become a z dependent, or it's not depend on x and y. So you apply curl E in a rectangular coordinate. Since there you have only x component, so you have only Ex, so Ez drop out, Ey drop out, Ez drop out, Ey drop out. And also since your Ex is depend on Z only, so this term also drop out. You have only partial derivative of Ex with respect to Z with the component Ay. So you have Y and differentiate of Ex over Z, where your Ex is the C exponential negative j omega square root mu epsilon. So you end up with negative j omega square root mu epsilon, and then Ex. Now you can see that from Maxwell equation, curl E equal to negative j omega. So you already have a negative j omega here. So this means if that satisfies the Maxwell equation, this term has to be the magnetic flux density B, which is equal to square root mu epsilon C exponential negative j omega square root mu epsilon, and the unit vector y, and that's become by, right? That's depend on z, or b equal to mu h. Now you check back if it's agree with the relation of E and H or not. From mu hy, that's equal to your B actually is this term, or you simply do B equal to mu hy, right? And also this term is actually your Ex. So you have your Ex multiplied by square root mu epsilon. That's why I have the term on the right of the equation become square root mu a Ex, and this one also equal to B, which is B equal to mu h, and your Hy become square root epsilon over mu Ex when square root mu over h, square root mu over epsilon actually is eta, or the intrinsic impedance of the media, and that's the agreed, with E equal to nu h, where h equal to square root mu over epsilon. So that's satisfy the Maxwell's equations for the case 1. Now let's move to case number 2. H equal to unit vector phi COR exponential negative j omega square root mu epsilon z, but you need to work on circular cylindrical coordinates. That means you need to work out on your curve, right? So what about the curve in cylindrical coordinates? Let's move to the next page. Okay. For the circular cylindrical coordinates, your curve h actually become this term. And for the h given, you have h only in the phi component, and your h phi depend only on r and z. Okay, so by considering this term curve h, you have only h phi, so this term drop, this term drop, this term drop, and this term also drop. And for h phi depend on r and z, you need to keep two terms. By doing differentiate, you pick up this term, right? And also this term. For your H, phi actually equal to A over R exponential negative j omega square root mu epsilon. So you have you do the integration, and for the second term, your R multiplied by H phi, so R cancel out, so you would end up with a constant. So this term also drop because you differentiate constant. And then finally you have curl H equal to unit vector R j omega square root of mu epsilon H phi. To satisfy the phasor forms of Maxwell equation, you have curl H equal to J plus J omega D, or D equal to epsilon E. This is the Maxwell equation. For shot free, you have sigma equal to 0, so this term, the term J drop. You have only your curl H equal to J omega epsilon E. From your curl H, you can compare, to this term, and you check back again if it's true or not. And finally, when you work out, you have the relation of E equal to eta H. Then the field is satisfied for the Maxwell equation. Now for electric field equal to unit vector theta, COR exponential negative j omega square root mu epsilon cosine theta in spherical coordinates. This is curl E for a spherical coordinate. Since your E has only your E theta component, so this term drop, ER drop, E phi drop, and also E thetas that depend only on R and theta. So this term also drop. You have only your phi component 1 over R, and you do differentiate d by dr r d theta. When you multiply R to E theta, you have only constant left. So this one also curl E equal to be 0. To satisfy the phasor forms of Maxwell equation, curl E have to be equal to negative j omega b, but for this case the curl E equal to 0, so this one is not satisfied Maxwell equation. Okay, here let's move to the next problem. Okay. Problem 3.12e. In each of the following, use a plane wave model to estimate the quantities for various laser systems. You have a system I, a small helium neon laser, lambda equal to 633 nanometer, typically produces 1 milliwatt in the beam. That's mean the power, right? With a beam of 1 millimeter diameter. Estimate strengths of electric field and magnetic fields in the laser beam. Okay, so you're talking about electric field and the magnetic field, and also the power. You know the average power PAV equal to 1 over 2 the magnitude of electric field multiplied by the magnitude of our magnetic field. If you take a look at the unit, your E electric field has the unit volt per meter, and H has the unit of ampere per meter. So V multiplied by A does give you watt, just like in your circuit, divided by meter square. So you have the power per area. Since E over eta equal to H, or you can compare to your circuit, E as the unit of volt, right? Volt divided by ohms, or V equal to or eta H. That means H has the unit ampere, and then eta has the unit ohm. Just like you have Ohm's law, V equal to AR. So you can represent H by E over eta. So for PAV, that's give you 1.5 the magnitude of electric field square divided by eta, where your eta equal to square root mu 0 over epsilon 0 in free space, or equal 120 pi ohms, or 377 ohms. So you can find the magnitude of electric field. That's equal to 2 eta, the power average 1.5. For the power given to be 1 milliwatt, so you have and you also have eta equal to 377 ohms. You just plug in numbers, you have end up with the magnitude of your electric field is 980 volt per meter, and your H is simply equal to the magnitude of your electric field divided by eta. So you have 980 divided by 120 ohms, pi. That's give you 2.60 ampere per meter. Now for system 2, it is very easy to focus on the power for a meter power carbon dioxide laser for lambda equal to 10.6 micrometer. That's the wavelength. So that there is the breakdown in air, taking breakdown strength as at low frequencies, about 310 to the 6 volt per meter. That's the electric field. Right? Estimate the power density in such laser beam. So we're looking for the power density. For the E given 3 to 10 to the 6 volt per meter, your P average actually EX squared divided by 2 eta. So it's just plug in the number where your eta is to become 377 ohms, or 120 pi ohms. That's give you P average to be 1.19 10 to the 10th watt per meter square. That's become the power density of the laser beam. For number 3, really high system 3, really high power in the class laser, lambda equal to 1.06 micrometer. That's your lambda is much less than the lambda of a carbon dioxide laser. As you have been used in laser fusion experiments, ask you to estimate electric field strength at the target for one producing 10.2 kJ in 0.9 nanosecond, focused to a target about 0.5 millimeter in diameter. So for the power in the term of energy, because the energy is given right in the unit of joule, so the power actually become the energy over the time over the area. So that's become the power density, right? P, or you can check for the unit, that's become joule per second per meter square. So your power actually, the power density is going to be just a plug-in number. The energy is given is 10.2 kJ. The T t is the 0.9 nanosecond, that's the 10 to the negative 9th second, and the area is the pi r squared. You have a 0.5 millimeter in diameter, so your radius is the 0.25. 1/2 over 0.5 millimeter, 10 to the negative third. You can change the unit from millimeter to a meter. And so you have your P, the power density, equal to 5.8 10 to the 19th. And that's also equal to E squared over 2 eta. That's we worked out equation before. Just plug in the number, and the magnitude of your electric fields become 2.08 10 to the 11th volt per meter. Okay, so that's the problem 3.12e. Okay, for the last problem, 3.18b, a uniform plane wave of frequency 1 gigahertz has a power density of 1 megawatt per meter squared and falls upon an aluminum sheet. It can be shown that upon reflection from a good conductor, magnetic field at the surface of the conductor is essentially double that in the incident wave. It can be shown that upon reflection from a good conductor, magnetic field at the surface of the conductor is essentially double that in the incident wave. Estimated power absorbed in the aluminum per unit area, and note it as a fraction of incident power. This is straightforward. So you have the incident, the magnetic field, Hy equal to H0 exponential negative j k delta. That's the aluminum. You apply your P average, that's equal to 1 over 2 eta H0 squared. So you look for H0 when P, the average power is given. That's 1 megawatt per meter squared per area, and your eta is the 377 ohms or 120 pi ohms. So you have H0 equal to 72.8 ampere per meter. Now they say that if the magnitude field at the surface is double, so you just plug in instead of using H0, you use the 2H0 and multiply by RS. See the similarity. This eta has the unit of ohms, and RS, that's the surface resistance over the aluminum. From page 155 from the book, at URS for aluminum, that's going to be your 3.26 10 to the negative 7 square root F, whereas F is the frequency that's given to be 1 gigahertz. You just plug in the number. Now your P become 109.2 watt per meter square. So to find the fraction, you just simply divide P new by P average. For the new one, you have 109.2 watt per meter square, where you have to start the power density become 1 megawatt. That's 10 to the 6th. So you end up with the fraction to be 1.09 10 to the negative 5th. Okay, so for the next series, we're going to start doing problem at the end of chapter 4. Okay, bye.